Okay, good morning, everybody. Thank you for inviting me here. My name is Alessandro Scirè. I'm from University of Pavia in Italy, and the title of my talk today is Emergence and Criticality in Spatiotemporal Synchronization, the complementarity model. This talk is based on a recent publication that appeared in the Artificial Life Journal. And, sorry. Okay. The question I'm addressing is a very general question. How does collective intelligence emerge from many simple interacting units? It's a very general problem. There are many ways of addressing it. But from the theoretical point of view, one possible choice is active matter. Active matter consists of a population of dynamic agents that are given a source of internal energy. They used to deal with the interplay of both positional and orientational order, and they display the emergence of large-scale self-organizing behavior and emergent properties. A typical example is the Vixek model for swarming, and another example is active nematics for liquid crystals. But what I'm going to show is an idea that I had a couple of years ago, and I've created a new model for the interplay of positional and orientational order in active matter. This model first appeared in this publication a couple of years ago, and it is regarded as a new paradigm for artificial life. And it deals with the collective dynamics of two subpopulations of polar agents that I've called spins. They are separated into families that I've chosen two colors in order to represent those two families. The picture is the following. There is many spins that are moving in a plane, and each spin is characterized by 2 degrees of freedom, the position respect to the origin, and the orientation respect to a reference angle. The interaction is limited by a sort of interaction radius, so it decays with the distance. And the two families interact in this way. When different colors interact, they attract in space, but they repel in angle. So they try to align out of phase with an angle of pi. When two spins of the same color interact, they try to repel each other in space, but they align in angle. So it's a sort of complementary interaction scheme. That's why the name of the model. The model, from the mathematical point of view, consists of n with n that can be arbitrarily big, n coupled nonlinear differential equations, and for the time evolution of the degrees of freedom of each spin. Now, this function W is a potential well. That means that the interaction are kept local. They decay with the distance, and the distance interaction radius is 1. So I don't go too much into mathematical details. The thing that matter the most is this parameter delta, is the control parameter. In this kind of mathematical system, these this term acquires the meaning of a circular anisotropy. And the effects of that control parameter are first, it separates stable from unstable behavior. If delta is small, if delta is 0, the two colors align and converge, lock to the same position with an angle of pi. If delta is increased, the angle decreases, and when delta exceeds a threshold value of 0.5, this dipole become unstable, both in position and in orientation. So delta tends to make the red and the blue spin rotate in opposite direction. Makes the system active because it's what provides energy to the system, and creates local instabilities, both positional and orientational. And I will show that the delta actually drives a phase transition from order to disorder when delta exceeds these thresholds. Okay, so for simulation, I start from random initial condition in both space and orientation. So a situation like this. And when delta is very small, well below the threshold value, the system creates those dipole aligned like this in antiphase, more or less. This one is left alone, but the system slowly rotates in order. Now I make it fast because it's very, very slow. Okay. So all the dipoles are created like this, and on the long run, they display this spatial order. They tend to align in a situation that is more or less translational symmetry. Means it's a regular, almost regular kind of situation in space, while the orientational symmetry has been broken because they had to choose a specific orientation of the dipoles. This happens because delta also introduced a dipole-dipole repulsive force that is what create this spacing between the dipoles. Okay, if I increase a bit delta, still well inside the locking range, I see the appearance of different kind of solutions. I see the appearance of those loops, counter-propagating loops that are both transport loop and spin current loop. That means that the spins rotate and move in the circle, rotate in the circle and move in another circle, this one. And on the long run, the behavior stabilize in a more or less regular loop of spin currents. And on the outside, what they create is a piece of an anti-vortex. This is a topological defect. All this structure is a topological texture, and is made of two parts: the current loop and the point defect. Okay, now, so if I let those spins while they move, I let them paint the trajectory, what I find is something like this: a loop that is around the center of an anti-vortex. Okay, if I repeat the same simulation with the same value of delta, I find three possible solutions. The persistence of the homogeneous solution, like in the previous case, and the appearance of these point defects, anti-vortex and vortex. They usually go together. If there is one, there used to be the other one as well. With this transport loop pinned to the center. In both cases, the transport loop is pinned to the center of the defect. Here is an anti-vortex, here is a spiral or a vortex. Okay, but if on one side this kind of solution can be predicted from local properties, this other one is an emergent, is a collective behavior that cannot predict it from the local stability analysis of the local properties. And is split in two complementary parts, vortex and anti-vortex. Now, if I move delta bit always inside the locking region, I see high variability in shapes. Those kind of solutions repeat themselves, vortex, anti-vortex, vortex, vortex, anti-vortex. But there is, however, a high variability in the kind of shapes, even for the same value of delta, like in these two cases. This is a property that is called non-ergodicity, and it's typical. It may happen in chaotic system, but it's typical of problems that navigate a complex stability landscape like neural networks or protein folding. And in all those cases, I see the persistency of those loops of frictionless currents, similar to superfluids. So I perform a statistical analysis versus the control parameter. I introduced time-dependent collective parameter, the choice based on standard procedures in statistical physics, that is the translational kinetic energy, the rotational kinetic energy, and this order parameter that is called the Kuramoto order parameter that accounts for the phase synchronization. It's actually this parameter, the kinetic energy, that is able to discriminate the three kind of solution, because here with no kinetics is the regular static translational symmetric solution, while here this branch has to do with the vortex anti-vortex kind of solution. This is the local instability threshold, and after that instabilities starts to appear and the behavior becomes more and more chaotic. Okay, if I increase the system size, the scenario grows more complex. This is with 80 oscillators. With 200, I already see a proliferation of these vesicles. 500, I see now three vesicles. And if I have 1000, I start to see these kind of structure that are strange patterns that I don't have seen before in any kind of soft matter or active matter system before, in general in statistical physics or condensed matter or spin problem, spin texture, magnetic problem. As far as I know, is a new thing in a new kind of behavior. And now I show the movie of about how this kind of structure is formed from random initial condition. The structure is much big than the interaction radius. I mean, all this path is coordinated, but those oscillators that move here, they don't know anything about what happened on the other side. But this happened through after a long transient. They start like this. In the beginning, the loops start with a situation that show big changes in the spatiotemporal dynamics. So it's a slow process of self-optimization that starts with a turbulent initial situation in which the system like explores several possible configuration, creates loop, destroys loops, and after a long transient, the flow self-stabilizes in a network of currents that is this one. This is already a quite complex flow because the velocity in each arm is different, the orientation are different, so the system has to calculate how to sustain this kind of flow. And the final situation can be different. I don't know yet what is depends on. In this case, at some point the flow interrupt and self-destroy. After a phase of homeostasis where the flow is more or less stable, this simulation shows that this flow specifically stops abruptly at some point. I don't have yet understood the criteria for having a longer or a shorter stability region. Okay, now you see. At some point it just blows up. Okay, so there are three phases of the development. Glassy self-optimization, stabilization of the collective flow, and in some cases, a spontaneous death. I don't know yet how those three phases manage one to the other, one with respect to the other. But the collective parameters, time tracing, reflect this scenario. There is a first part of the glassy transient where there are big jumps in the kinetic energy. Here, this is logarithmic scale, so those jumps are actually big. Big changes in the synchronization and big peaks in the collective frequency. In the middle, a phase of homeostasis where the parameters are more or less constant or show smaller variation or peaks with power law statistics. This is multiplied, amplified. These peaks will be much smaller. And when the network dies, the kinetics goes down and everything stops. It sounds to me like a form, it reminds me what is liquid-liquid polymer condensation. Okay, in conclusion, I've introduced a new agential model for the emergence and self-organization of complex synchronous spatiotemporal patterns. I didn't show it, but those patterns are very robust to perturbation and to noise. And if I try to break the current here, the system self-repair easily. And they display long range coherence, much longer than the interaction radius. Those patterns display the image of regulative plasticity because they are able to self-regulate, they modify in order to um, be able to regulate the traffic in real time and modify the velocities in the arms and the angle in such a way to support the flow along all the structure, which is decentralized and self-developed. And they also show complex statistical properties like glassiness, non-ergodicity, multifractality, and power law statistics. I didn't show too much this because I didn't have time, but in the publication there are more details. Okay, this is more or less what I have to say today. So I thank you for your attention.